chapter, that the particular nature of matter. Okay, let's do that part. Okay.
Yes, ma'am.
Before that, please give me a brief about how much you are aware as a part of thermodynamics. Here we will do the study of thermodynamic chapters. Okay, the heat exchange.
Yes, ma'am. Yes, ma'am.
Yeah. Yeah. Give me.
Uh,
How much you are aware that thermodynamics. Yeah. Okay, go ahead.
particle. I think like I kind of solved few questions with the ones with the available formulas from the data booklet, like all those. But
Hmm.
I'm not like confident with the graphs part of
Mm-hmm. Mm-hmm.
how like the graph would be like something like between volume and uh, pressure, something like it has like various graphs. 1 second, ma'am.
Mm-hmm. Yeah, it's okay. It's okay. Go ahead.
But I kind of like I am like familiar with the specific heat capacity and all those stuff. Like I think like I
Hmm.
am not when I solve this, if there is given in
Mm-hmm.
the question, then
Hmm.
I can solve it. But if there is a explained question,
Hmm.
that part I will kind of struggle with that. And then also
Mm-hmm.
the MCQ part, like uh I struggle with the graphical representation. I think that's the thing which I wanted to say.
Okay. Fine. But I am asking, like, you, whatever you said is perfectly correct. Just do let me know how much you are aware in thermodynamics. That is my question, bache.
Like a concept wise, ma'am, like which
Mm-hmm.
I know which
Mm-hmm.
stuff
Mm-hmm.
I know.
Yeah, exactly. Concept wise.
Then I think I'm kind of familiar with B1. B1.
Okay.
I just need to revise it, but I know the like concepts.
Okay. Yeah, I'm listening. Go ahead.
I'm just checking my textbook now. 1 second.
Acha. Do it.
Yes, ma'am. The gas loss, right? Gas loss. Yeah. That's where I struggle. Like that, my concept clarity is not clear in gas loss, ma'am.
Okay. Yeah, I'm listening. Go ahead. Am I audible, Akshita?
Yes, ma'am. Yes, ma'am.
Yeah. Say, I'm listening.
So I think like we can start with B.3.
B.3, you don't want to go with B.1 and 2?
Yes, ma'am. I think I know the like theory parts, and I
Oh,
know the
very good. That's why I was asking it, that if you are aware of the basics, then I will go with a very huge flow, no? That's why I'm
yes,
asking you. So
yes,
you
ma'am.
are aware of like B.1 and B.2. Say B.2 though is very easy. It's just the carrying the waves part only, right?
Yes, yes,
That
ma'am.
is your greenhouse effect and everything. If you want,
Yes,
I will actually catch these chapters in the last if I get the time. I will repeat at a very fast pace. Okay, don't worry.
yeah, ma'am. Sure, ma'am.
Okay. So right now I'm starting with B3, and that is the laws. Okay. Just have a look over here. What are the gas laws which are been given in our textbook? So as per this textbook, okay, that is your syllabus. What has been said, that we have uh three gas laws, okay, and we have the mole concept and the Avogadro concept, okay.
Yes,
So what
ma'am.
does the mole concept says? The mole concept says, Akshita, that we have one standard atom which is known as carbon 12 atom, okay. In this carbon 12 atom, if I compare it with the mole, my 1 mole of atom of carbon 12 carries 6.023 into 10 raised to 23 atoms.
Yes, ma'am.
Okay, like if I'm weighing something, let's say 1 kg weight I'm having, and I'm weighing it with potatoes. So potato will come, let's say, nearby 12.
Yes,
Okay,
ma'am.
so these
Yes,
potatoes I'm comparing with some standard term, let's say 1 kg weight. So similarly, in our molecular study also, what do we do is we compare something standard one with the molecules of other particles. So my standard part over here is carbon 12 atom. Understood or not?
yes, ma'am.
Okay, so this carbon 12 atom basically shows me that it has 6.0323 into 10 raised to 23 atoms. And when I compare it, it is basically 12 gram. So in grams, it is 12. In numbers, it is this much. And in moles, it is this much. Understood the comparison?
Yes, ma'am.
1 mole carries 12 gram. Also, it carries 6.023 10 raised to 23 atoms. So,
Yes,
this is in number of atoms, this is in grams, and this is in moles.
yes, ma'am.
Okay. Now,
Yes,
this thing is known as Avogadro number and it is fixed.
yes, ma'am.
Understood?
Yes, ma'am.
Any doubts?
No, ma'am.
Okay, great. So, if suppose I ask one question as that, wait, say I am saying this question. If a mole of carbon has 12 gram, how many atoms of carbon are there in 2 gram? Can you solve this?
Yes,
Unitary
ma'am.
method, very easy. Okay, just
Number of
1 minute of the time I'm giving you. Be quick.
one second. I'm just recollecting my formulas, ma'am. Since I don't have my physical data. One second.
Oh, I'm sending it to you. Shall I?
Yeah, sure, ma'am. Sure.
Okay, yeah, I'm sending it to Miss Sonia. And do we have any chat box over here also?
Uh, yes, ma'am. I
Can
think
I
we have
send them?
Zoom. The Zoom chat.
Yeah, so that I can send you something. Okay, okay, check. There it is gone. Chat box. I should send you
I think we
file.
can send a file. File.
Yeah. I got it. I got it. On the desktop, I'm sending you.
Mm.
Check. I had sent you the data booklet also. Okay.
I haven't received it, ma'am. I will just yeah. Now I think yeah, I received it.
Did you got it now?
Yes, ma'am.
Okay. Go ahead. Be quick.
It that one was number of moles is equal to number of like mass by molar mass. Is it that one, ma'am? the question? Can you share the question again? The Can you show the question? If a mole of carbon has a mass of 12 gram, how many atoms of carbon are there in 2 grams? N is equal to N by Na.
Yes, Akshita. What you were saying?
Uh, I, I think we are going to use N is equal to N by Na, that formula. And then,
Oh, you will run with this unitary method only, no? One mole contains 6.023.
yes, ma'am,
Okay?
that one, the formula, like, it has Avogadro number in it. Like,
Yeah, exactly, exactly. Go ahead.
ma'am, it is 1.004 into 10 to the power 23. Ma'am? Hello, ma'am? Hello, ma'am? Ma'am? Can you hear me?
Yes, Akshita, say.
Ma'am, it is 1.004 into 10 to the power 23.
Mhm. No, it is 1.003 into 10 raised to power 23 atoms.
Yes, ma'am.
Correct? Uh-huh,
Yes,
correct, correct, correct. Okay, that is correct. So basically, you are aware of these formulas, right?
yes, ma'am.
Okay, very good. Now we will define the next part, and that is the ideal gas. Okay, listen here very clearly. So, what is the ideal gas?
I just know the formula PV is equal to NRT.
Yeah, basically, we run with the formula PV equals to nRT, and here are some basic things that we need to keep in mind. Okay, that I am sharing with you. Just check. Uh, Okay, check. According to our simple model, a gas is made up of large number of perfectly elastic tiny spheres moving in random direction. See, one thing, Akshita, it is a completely ideal gas. It is not existing at all in the nature. Okay, we
Yes,
are taking a standard case of the gas that we call it as ideal gas. Okay,
yes, ma'am. Yes, ma'am.
so the ideal gases are not existing on the surface of earth or in the atmosphere. Done. So the collisions between molecules are perfectly elastic between them. We assume all these things, that
Yes, ma'am.
they show a perfectly incompressible nature. You cannot compress it via applying any elasticity, via applying any temperature, via applying any volumetric things, via applying any pressurized things like that. Understood or not? Their
Yes,
molecules are completely identical in nature with each other. They do not have any force of interactions. Okay, we take all the standard case, Akshita, over here. Are you getting?
yes, ma'am. Yes, ma'am.
For ideal gas. I'm explaining this for ideal gas. Okay, so
Yes,
everything we are considering here in the ideal gas as to be the, what do we say? We consider these things with the standard things. Okay, like in oxygen, the force of interaction is how much, then how much they can be compressed, then how much volume does they carry, like that. Understood?
yes, ma'am.
Okay. But here, what do we have is in mind that all the time the collision between the molecules are perfectly elastic. The
Ye-
molecules are spheres. The molecules are identical. There is no force of attraction between the molecules. This means that the molecules move with a constant velocity. The molecules are very, very small. That is, their total volume is much lesser than the volume of the container. This means that if suppose this is my container and throughout I am having the molecules of ideal gas, okay, and then I collect it at one place. Let's say I had collected it over here. So at this place, the volume whatever it had occupied will be very much lesser than the volume it is occupying here. Understood?
Yes, ma'am.
Understood? So the
Yes,
molecules are very small. Their total volume is much lesser than the volume of the container. Understood?
yes, ma'am.
So they may ask you that which hypothesis or which postulate support the volume of the molecules. So you have to write this hypothesis. These five hypotheses you have to keep in mind. You have to memorize them. Understood or not?
Yes, ma'am.
Any
Yes.
doubts?
No, ma'am.
Okay. So now next part is your, okay, what are the formulas? Let's have a look one by one. Okay, so how do you define the state of a gas? So the state of the matter we need to give, uh, in which basically it takes the shape of the container. Okay, and the molecules are randomly moving in any direction. So these are the properties of gases that we had studied already in the fifth, sixth standard, right? Then
Yes,
what is
ma'am.
the formula for volume? What is the formula for temperature? So we are having certain formulas. Suppose I am trying to find the temperature, then you will define it as average kinetic energy, which is 3 by 2 kT. So from here you can find out the temperature formula, that is this one, correct? Where K is the Boltzmann constant, value is 1.38. into 10 raised to minus 23 joule per Kelvin. Okay.
Yes, ma'am.
Okay, this is the formula to find the temperature. Okay,
Yes, ma'am.
and this is average kinetic energy. Understood?
Yes, ma'am.
Done? Okay, yeah. Then we have suppose n number of molecules in a gaseous system. Then your formula will be n multiply average kinetic energy equals to 3 by 2 n times kT. Okay, this is in terms of moles. This is in terms of molecules. Any doubt?
No, ma'am.
Sure?
Yes, ma'am.
Okay. Now let's find the formula for uh, pressure. So for pressure, we have the formula force over area. Okay. And from here we define as 1 Pascal as 1 Newton per meter square. Clear?
Yes, ma'am.
Okay. Now, the pressure can also be given as rho GV. Remember?
Yes, ma'am.
Yeah. So the formula for pressure can also be defined as like that. Okay. And if suppose the gaseous molecules are moving in a random three dimensions, then you will define it as 1 by 3 rho V square, where V is the velocity, rho is the density. Okay.
Yes, ma'am.
Understood or not?
Yes, ma'am.
Yeah. So this is also the formula that works. No need to give all these formulas at one time, because you are also aware that these formulas are given in your formula booklet. Okay. And you can use them. Done? Any
Ye-
doubts?
No, ma'am.
Okay. Now we have 2, 3 laws that are defining the laws of gases. They are basically, they are known as the law of gas. Okay. So let's do that part also. Just give me a sec. Yeah. Check here. Laws of gases. Okay. So I'm
Yes, ma'am.
defining it one by one. Just do write it wherever you are putting your notes. Okay. Done.
Yes,
So the very first law is Boyle's law. Okay. The very first law is Boyle's law. Boyle's law work at constant temperature. Done. And what
yes,
does it convey? That at constant temperature, pressure is inversely proportional to volume. How much high the pressure you are applying, low will be the volume it becomes. Understood, Akshita?
yes, yes,
Okay, great. So higher the pressure, lower is the volume. Done. Now, as per Boyle's law, whenever you are drawing the graph, your graph will be drawn like this. Okay, if this is the pressure and this one is, it goes with two system.
Can you repeat, ma'am? The voice kind of like broke down.
Lagging.
Yeah, it's laggy.
Okay, I am saying pressure is inversely proportional to volume, so the graph will be like this.
Yes, ma'am.
Understood? No. So
Yes,
if
ma'am.
we have two systems over here, then you will say that my P1 V1 will be equal to P2 V2, but condition applied at constant temperature. Okay, any
No,
doubts?
ma'am.
Sure.
Yes, ma'am.
Now let's take the next thing. The second law is known as Gay-Lussac's law. According to, okay, did you understood the thorough postulates of ideal gas?
Yes, ma'am.
Okay. So what does the Gas-Lussac's law suggest? It suggests at constant volume. Okay. And what does it convey? It conveys that pressure is directly proportional to temperature. Okay. So higher the pressure, higher will be the temperature. Done?
Yes, ma'am.
Okay. So when you draw the graph for this, you will going to get your graph something like this. Okay. Here is the pressure and here is the temperature. And if we have two systems, okay, then what should be the thing? That your P1 T1, wait, yeah, P1 over T1 is equal to
P2 by T.
P2, yeah, or even you can write it as P1 T2 is equal to P2 T1. Understood?
Yes, yes,
Okay. So
Yes.
after this, we have Charles' law. What does the Charles' law says? Charles' law says at constant pressure. Okay. And what does it convey? It basically conveys of us that yeah. So it says that volume is directly proportional to temperature. Okay. So the graph will run as per Charles' law like this again. This is volume and this is temperature. So higher is the volume, higher is the temperature, but your pressure needs to be very much constant. Understood?
Yes, ma'am.
Okay. So basically, this thing can also be defined as V1 over T1 will give you V2 over T2, or even I can write V1 T2 is equal to V2 T1. Clear? These are
Yes.
the formulas applicable for two systems. Done. Now after this we have got, by combining all these laws, we have got the gas law. Okay, what were the laws? I'm writing once again over here at one time. Okay, so Boyle's law suggests us that pressure is inversely proportional to volume. Gay-Lussac's law suggests us that pressure is directly proportional to temperature. Then we have the Charles law, which suggests us that
Pressure is volume is proportional to temperature.
yeah, exactly. Okay, so volume is yeah, volume is directly proportional to temperature. Now combining all these law, I will get PV equals to nRT. Okay.
Yes, ma'am.
Okay, where P is the pressure of the gas, V is the volume of the gas, N is the number of moles, and R is the constant value which is having 8.31 per mole per Kelvin. Okay,
Yes, ma'am.
done. And T is the temperature of the gas. Even you can write it as PV equals to NKBT.
Yes, ma'am.
Okay, so here N is the number of molecules. You will apply these formulas, Akshita. When the number of molecules is given, you will apply this formula. When the number of moles is given, you will apply this formula
Okay,
in
ma'am.
the question. Understood or not?
Yes, ma'am.
Okay. Likewise, I will give you one question and I'm explaining it. Just write down till that point these things.
Yes, ma'am.
Okay. So the question is this one.
The pressure of the gas inside a cylinder is 300 kilopascal.
Hmm. Yeah.
Pressure.
So
Gas
how
is
we will going to solve this?
what will be
See, we will write first in the exam all the things which are given. So 300 kilopascal with the
yes,
SI unit you will come to know. Okay. Then
yes,
if the gas is compressed to half of its original volume, the temperature is 327 minus 27, right?
yes, ma'am.
Okay, that you will get the answer. Then after this we have volume which had become half of the original volume, correct?
Yes, ma'am.
Okay, so we need to calculate what will be its new pressure. So how we will do? We have the formula PV equals to nRT, right?
Yes, ma'am.
Okay, so uh, at the beginning, I think my this value nr value will be PV over T, correct or not?
Yes,
N
ma'am.
and R both are constant or not in both the cases?
Yes, ma'am.
Okay, So in the beginning it is, and at the end also. Okay, so in the beginning I'm comparing to at the last. Making sense? Any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Okay, so now I'm calculating this. So this is PV over T before, this is PV over T after. Done?
Yes, ma'am.
Okay, so I think it will become pressure is not given over here. PV over T in the beginning was given. Pressure not given. Volume had become half. Temperature has become how much?
300.
Temperature rises from this to this. Okay, 300. Okay, so this has been done.
Yes, ma'am.
So what it will become? Is it going
Three.
correct? What will be its new pressure be? That 300, the gas is the half of its original volume. Okay, so what it will become? In the start, is there any pressure given? 300 kilopascals is the temperature here
Yes.
given,
Yes, ma'am.
isn't it?
Yes, ma'am.
So it will be 300,000, right?
Yes.
Volume will remain as it is. Temperature was 300 in the start. Okay, after the temperature also, what will be its new pressure be? The gas is compressed to half. Okay, so if you compress the gas to half, that means pressure is half, so volume will be double, no? Sorry, temperature will be temperature will also be increased, na? Because here what is the thing which is constant? Pressure.
Yes, ma'am.
Sorry, yeah, exactly what is happening is, as per these laws, if I apply PV equals to nRT, so if you are raising the temperature, your volume, or I should say your temperature should also get rise.
Yes, ma'am. So it
So how
will
much
also.
the temperature will going to get rise? Because see, pressure is directly proportional to temperature. So if I'm
Yes.
raising the pressure and my volume is becoming half, so my volume is inversely proportional to, where is the formula? Yeah, volume is inversely proportional to pressure, isn't it?
Yes, ma'am.
So if I'm decreasing the pressure and I'm making it half, then I think the temperature will become double over here. It will become double, isn't it?
Yes. Yes, ma'am.
Are you getting or not?
Yes, ma'am.
Getting these things? Okay, so I think it will
Yes.
become P into V over 2 over 600. Correct?
Yes.
Let's calculate them. 300,000 multiply V over 300 equal to P into V over 2. We have to find this is V. I get cancelled out. I am only remaining with the half over this. So I think it will become P over 2 over 3, 600. So P over 2 over 600. So it will be P over 2 multiply 1 over 600. Isn't it?
Yes, ma'am.
Okay. So further simplifying them, what will I get?
We
Yeah. So just write down the pressure as the main content over here. Okay. So that means my pressure will be 3
3
lakh thousand
by.
multiply 600 multiply 2 over 300. Check. Now am I correct? So 6,
Yes.
300 2s are 2 2s are 4, 4 3s are 12. So I think it will get 1200,000 Pascal, or I
One,
will
two.
get 1200 100 kilopascal.
Yes,
Correct?
ma'am.
This is the new
Yes, ma'am.
pressure. Any doubts?
Uh,
Now,
in that
yeah.
uh, in that part alone, like I was little bit confused, ma'am.
Where?
Where was? One second, ma'am. Can you scroll up? Yes, ma'am.
Mm-hmm. Check. Pressure in the start was 300 kilo. Temperature
Yes.
has got risen up to 300. Okay. Okay.
Can you like write the relation, ma'am? Because the relation alone I am confused. The how
Okay.
it came into it.
So pressure is inversely proportional to volume. So if
Yes,
I put my volume as half, so my pressure will become double,
yes, ma'am.
isn't it? Okay.
Yes,
So here volume have got half, or what did it got half? Volume got half. So pressure is inversely proportional to volume. Check. So my
yes, ma'am.
pressure will become double. So this is what I had put.
Okay, ma'am.
Any doubts now?
No, ma'am.
Sure.
Yes, ma'am.
Okay. So this is what I had put over here, that my pressure will become double. Okay. Now let's do the next portion, and that is the internal energy of the gas. Okay, Akshita.
Yes, ma'am.
Okay. How much knowledge do you have about the internal energy of the gas? Tell me.
Internal energy. One second, ma'am. Internal
Hmm. Go
energy.
ahead.
Can you like? I don't remember it, ma'am. Like, can you like give me any
Perfectly fine.
hint?
Basically, the molecules have what happens is the ideal gas is made up of large number of perfectly elastic, I should say, the molecules, right?
Yes,
This is what we have imagined, right? So when the
yes, ma'am.
molecules collide, their momentum and energy both are conserved in that.
Yes, ma'am.
Okay. But between the collisions, there is no force acting between them, and hence there is no work done, because obviously I had told you that there is no force of interaction between them.
Yes, ma'am.
Remember? Okay.
Yes,
So what happens is, if suppose the molecules have no potential energy, then the total kinetic energy of the molecules will only be remaining with them. Making sense?
yes, ma'am.
Okay. So when only that much of energy is remaining with them, that we call it as internal energy of the gas. Okay.
Oh,
So when I define it, I'll be writing the definition for internal energy as the total kinetic energy of all the molecules is called internal energy of gas. Understood?
yes,
To derive this, we know that the average kinetic energy is given by 3 by 2 kT. Remember?
yes, ma'am.
Okay. Where K I had told you as the gas constant, Boltzmann constant, which is 1.38 into 10 raised to minus 23 per Kelvin. Okay.
Yes, ma'am.
Yeah. So the 1 mole of gas contains 0. Avogadro number, that is 6.023 10 raised to 23 molecules.
Yes, ma'am.
1 mole contains
Zero.
6.023 into 10 raised to 23.
Yes, ma'am.
Correct?
Yes,
Done.
ma'am.
Now, if suppose I have n number of atoms in this, okay. Suppose I have, let's say, if I'm calculating it in the terms of molecules, okay, then it will be having nearly this much of molecules. Okay, so I
Yes,
can also rewrite it as, if any number of molecules are being contained inside this, then I can rewrite it as that my average kinetic energy is equal to 3 by 2 Na kT. Okay, this only I had defined, Akshita.
yes, ma'am.
Okay,
Yes,
where
ma'am.
Na is the Avogadro number.
Yes, ma'am.
Okay, this is Avogadro number. Understood or not?
Yes,
So the
ma'am.
total kinetic energy, any doubts?
No, ma'am.
Okay, so the total kinetic energy for 1 mole of the gas can be equals to 3 by 2 RT. Okay, where
Yes,
R is the gas constant. Okay, where R is the gas constant. Done.
yes, ma'am.
Okay, so let me write that thing for you. Now, when you define the internal energy of the system, U, it will be defined as 3 by 2 nRT, right?
Yes, ma'am.
Why? Because I had told you that the total kinetic energy here is how much? 3 by 2 RT. So the total energy here, it will be nr 3 by 2 nRT, correct?
Yes, ma'am.
What is small n? Where small n is the number of gas molecule, number of moles.
Yes,
Total will be given like this only, no?
yes, ma'am.
Any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Okay, what did I told you from the start? Let's begin. I am saying, Akshita, internal energy is the kinetic energy of the total molecules.
Yes,
Let's
ma'am.
start calculating. Average kinetic energy is 3 by 2 kT. Now, in 3 by 2 kT, 1 mole contains these many number of atoms. So, for 1 mole, it will be 3 by 2 NaKT, right? So,
Yes,
the
ma'am.
total kinetic energy of 1 mole will be 3 by 2 RT. What is R? Na into K.
Yes, ma'am.
Okay. Avogadro number multiply K. Both the things are constant, Akshita. Na is 6.023, K is this much. Okay.
Yes, ma'am.
Got my points or not? So
Yes,
I had
ma'am.
written it like this. Okay. Now after this, we are calculating internal energy. Why? Because internal energy defines us that it is the total kinetic energy of all the molecules. So the total energy is this much. It is number of moles. Done. So therefore, I will get for a fixed volume. I will get Q equals to delta U, where my Q is the temperature or heat energy of the gas. Okay. So I will say for a fixed volume, when the heat is transferred, okay, it will
Yes,
increase the internal energy and hence the temperature of the gas also. Isn't it?
yes,
So
ma'am.
if there is no heat loss, Akshita, my total heat energy will be my total change in the kinetic energy observed in the gaseous system. Understood?
Yes, ma'am.
Now any doubts?
No, ma'am.
Sure.
Sure, ma'am. Sure.
Okay. So let's take one question over this.
Yes, ma'am. Hello, ma'am.
Yeah, I'm here. What happened? I'm
Ma'am.
pasting the question.
Yeah, ma'am. Suddenly the voice went, so I thought like again, the voice again like,
No, no, I was pasting. I was pasting. I'm not writing anything. Don't worry.
okay.
Yeah. Is it visible?
Yes, ma'am.
Okay. So basically, if I calculate this, I think 500 joule of the thermal energy. Second. Okay. What it is written, Akshita? 500 joule of the thermal energy is transferred to 2 gram of the helium gas.
Yes, ma'am.
Okay. And it is kept at the constant volume. So you have to calculate the temperature rise. So definitely Q equals to delta U formula we will apply.
Yes, ma'am.
Okay. Now let's check how we will do it. Okay. So we will apply that in this particular thing. It has been given as that for helium. We are aware that the molar mass is 4U.
Hydrogen. Yes, ma'am.
Yeah. And they had given 4 gram. They had given 500 joule of energy change for 2 gram of helium gas. Okay.
Yes, ma'am.
Check. Check. Isn't it?
Yes, ma'am. Hello, ma'am.
Yeah.
Yes, ma'am. Yes, ma'am.
Okay. So basically, this will be written as 4 gram and my number of mole will be 0.5 because for helium 4 gram is the molar mass, right?
Yes, ma'am.
Correct or not?
Yes,
N
ma'am.
is 1, and if they are asking 2 gram, my N will become 0.5. Any doubts?
No, ma'am.
Okay. Now I will calculate the increase in internal energy. Okay. So what will be the increase in internal energy? 3 by 2 N R delta T. Correct?
Yes, ma'am.
Okay. So let's calculate that part also. So here I will be getting that my 3 by 2 NR delta T is nothing but total energy is 500 joules. So my delta T will be 2 into 500. Just check what I am doing. Okay. 3 into 0.5 into 8.31. Correct? So it will become 80 Kelvin. Any doubts,
Yes, ma'am.
Akshita?
No, ma'am.
Clear?
Yes, ma'am. I'll just write this part down once again.
Yeah.
Yes, ma'am.
Are you done?
Yes, ma'am.
Good. So after this, we will be having the real gas assumptions. Okay, now let's come to the part and compare them with the real gases. Okay, So whatever assumptions, Akshita, we made when developing the model for the ideal gas do not fully apply to the real gases. Okay,
Yes, ma'am.
Akshita, any doubts?
No, ma'am.
Okay.
Because hypothetical, this
Yeah,
is,
that is hypothetical, no? And this is
yeah,
the
that
real
won't
gas.
work. Yeah.
Yeah. So like here, if we lower the pressure, the temperature becomes high. At high pressure, the density of the molecules can be close together. Okay. So the assumption of the volume of the molecules is negligible, does not apply in the real gas. Agree or not?
Yes, ma'am.
I'm saying at high pressure, see, they do not apply fully to the real gases. I'm giving you one example. Let's say I have lowered the pressure, so the temperature will become high. If I lower down the pressure, the temperature of the gas will become high, Akshita. Getting?
Yes, yes, ma'am.
Okay. So if I'm lowering the pressure, if the temperature becomes high, and at high pressure, the density of the molecule cannot be that much close together, that the assumption we made there. What was the assumption? That the volume of the molecules is is basically negligible, right?
Yes, ma'am.
In
Yes,
comparison to the volume of the container. Remember
yes, ma'am.
the last
Yeah,
postulate I had told you? Remember or
yes,
not?
yes, ma'am. I remember.
Okay. Okay. So they does not apply over here, because here if you try to lower down the volume very much, then the temperature will be raised and ultimately it will blast, no? So in the real gases you cannot do that much, isn't it?
Yes, ma'am.
Okay. But can basically at low temperature also the gas can change into liquid, and but obvious reasons they does not behave like gases. So this to be wrong, because here we are making the assumption for the gas, not for liquid. Making sense?
Yes, ma'am.
If you lower down the temperature, Akshita, what will happen?
Your voice is a bit breaking, ma'am.
Still it is
Hello?
breaking? Yeah,
Yeah,
hello.
now it,
Am I audible?
now, yes, ma'am. Y-
Oh,
Yes, ma'am.
okay. So I am saying, yeah, you are audible. Don't be.
Okay, ma'am.
Am I audible?
Yeah, yeah. Now it's clear, ma'am. There's no lag.
Okay. I am saying that if you lower temperature for gases, okay,
Yes, ma'am.
okay, Akshita, yeah. Then what happened? Basically, all of your, I should say that things, uh, the gaseous system will convert into liquid.
Yes, ma'am.
Okay. So if the gaseous system is converting into liquid, was what does it convey?
Ma'am, your did the screen go?
Yeah, I had done that.
Okay.
Okay, don't worry. I had done that because this chapter got over. Okay?
Really, ma'am? Oh,
Yeah. Okay. So
yes, ma'am.
basically what I was trying to convey is that if suppose your you lower down the temperature, the gas converts into liquid, and hence it does not follow any more rule for the gases, right or
Yes, ma'am.
not?
Yes, ma'am.
Okay, so now it does not applicable that we are applying the ideal gases law,
Yes, ma'am.
right? Yeah.
Yes, ma'am.
So this is how it works, Akshita, that everywhere the ideal gases law does not apply to the real gases. Okay, and whatever
Yes,
we have sorted, that was enough, and this chapter is over. Okay,
yes, ma'am.
and my humble request is, Akshita, please go through all the laws
Yes, ma'am.
and
Sure,
solve
ma'am.
at least 2 3 questions. Okay, Akshita.
Yes, yes, ma'am.
Gas laws only, solve some questions. Okay.
Yes, ma'am.
Okay, Akshita. Bye. Have a nice day.
Bye, ma'am. Thank you, ma'am.